My name is Monisha and I'm from University Malaysia of Pahang, and my research is about characterizations of water in crude oil emulsion stabilized by UMP surfactant NS1902. Let us begin with the background. Emulsions of crude oil and water can be found in hydrocarbon reserves, wellbores, surface infrastructure, transportation networks, and refineries. About 2/3 of the world's crude oil is produced as emulsions, which must be processed before being sold. Some oil containing significant amount of asphaltins do not produce stable emulsions, so resins and compounds with surfactant properties plays a major role in the production of a stable emulsion. The oil-water interfacial properties are modified by the use of chemicals such as surfactants and enhanced oil recovery technology. There are actually other number of valuable characterization studies on the stabilized water in crude oil emulsions through different technologies using different types of surfactants, which provide the evidence on several factors such as temperature, density, viscosity, surfactant concentration, chemical composition of crude oil, oil phase, and water content. However, none of these studies provided the study of characterizations of emulsion that is stabilized by UMP surfactant, which is a natural surfactant. In previous studies, they have used commercial surfactants, which are actually costly and will cause environmental issues. The presence of water in crude oil being produced is undesirable because of problems such as foaming, pipeline and tank corrosion, and increased power consumption. So these surfactants appear to improve the emulsion stability by adsorbing at the water-oil interface and forming a rigid film around the water droplets. So the main aim of stabilizers is to prevent the water droplets from coming in direct contact with the transportation pipeline surface. Other than that, commercial surfactants are also costly and they're not very environmental friendly. The main aim of this research is to investigate the potentials of UMP surfactant in stabilization of water in crude oil emulsions, to characterize the formulated water in crude oil emulsions in terms of physiochemical properties, and to compare the performance between UMP surfactant and other commercial surfactants. In order to achieve the research objectives, the scope of this research focuses on physical characterization of the formulated crude oil and water in oil emulsions through density, viscosity, water content, pour point, and interfacial analysis. Second is the investigation of the efficiency of different water to oil ratios, which is 20:80, 30:70, 40:60, and 50:50. Third will be the investigation of the efficiency of different types of surfactants like SPAN 80 and Triton X100 that are commercial surfactants, and UMP surfactant that is a natural surfactant. And the fourth one will be the investigation of the efficiency of different surfactant concentrations of 1.5, 2.0, and 2.5 on the stability of water in oil emulsions. Materials needed for this experiment are crude oil, and the crude oil is obtained from Petronas curd tape. We also need 3 different types of surfactant, that is UMP surfactant, Triton X100, and SPAN 80. For agitation, we need the 3-blade propeller. The method used in this study is agent in oil method. The agent in oil method will be used to prepare the water in oil emulsions. Water will be gradually applied to the mixture after the emulsifying agent has been dissolved in the continuous process, which is the oil. We will begin by preparing the crude oil and placing them in a beaker with specific volume according to the ratio. Step 3 will be adding the surfactant with certain volume according to the concentration. Step 4 will be adding the water gradually, and the volume of water will be according to the ratio as well. Then, using the 3-blade propeller, the emulsion will be agitated at 28 degrees Celsius for 7 minutes at the rotational per minute of 1800. Step 6. Once the emulsion is prepared, 1 drop of the emulsion will be placed on the filter paper to test whether the emulsion is water in oil or oil in water. If the emulsion did not form a large moist film on the filter paper, it will be oil in water emulsion. Therefore, we have to repeat the previous steps in order to get water in oil emulsions. Step 7 will be the bottle test. The amount of water that has settled to the bottom of the beaker will be measured using the scale on the test at 2 hours, 4 hours, 1 day, and 2 days. The separation efficiency from the volume of water observed in the beaker will be used to measure the amount of water separation in percentage. Significant amount of water will be added to the emulsion and shaken well and left to be separated. For the viscosity, samples of the emulsion will be tested using the digital dynamic viscometer with different rotational per minutes. The last step will be plotting graphs using bottle test results and the viscosity. The first graph shows the comparison of three different concentrations, which is 1.5, 2.0 and 2.5 when using UMP surfactant and the 50-50 water to oil emulsions. We can see that the lower separation percentage is by the 2.5 volume of surfactant. The higher the concentration of surfactant used, the lower the separation percentage of the emulsion. The higher concentration will result in lowering of coalescence of water. So when coalescence of water is low, the water droplets will join together slowly, and this will increase the time of separation of the crude oil emulsion. Thus, the emulsion will stay in its form without separating when there is higher concentration of surfactant. The second graph shows the comparison of water in crude oil emulsion stabilized by UMP surfactant with different water to oil ratios with 2.5 volume of surfactant. The volumes of water in oil has significant effect on the properties of crude oil emulsions, and from the second graph it is observed that the 20 to 80 of water to oil ratio has the lowest water separation percentage at the 24th hour and the 48th hour. The decrease in water content lowers the water droplets, therefore the lower water content ratio gives better stability of crude oil emulsion. From the third graph, it is observed that using UMP surfactant to stabilize the emulsion has gotten the highest viscosity at 1 rpm than using SPAN 80 and Triton X100, which is 248.1 and 201.2 at the same speed. This proves that the emulsion with higher viscosity is more stable. The pour point of UMP surfactant is the lowest, which is at negative 19.5 degrees Celsius compared to Triton X100, which is 66, and SPAN 80, which is 45 degrees Celsius. The HLB, hydrophilic lipophilic balance values are all available for the non-ionic surfactants. The lower the HLB value indicates the surfactants are lipophilic, therefore it works better for water in crude oil emulsions, while the higher HLB value for surfactants like Triton X100 is well suited to stabilize in oil in water emulsions. So considering the viscosity and the HLB values, UMP surfactant shows the most effective surfactant to be used to stabilize the crude oil emulsions.
Among the three surfactants, UMP surfactant is the most effective and has the most reasonable cost compared to commercial surfactants like Triton X100 and SPAN 80. From this investigation using various concentration of surfactant, 2.5 of the surfactant volume exhibited the most stable emulsion by having the least water separation percentage during the gravity test. The water volume fraction plays one of the major roles in stabilizing the crude oil emulsions, and from this study it is obvious that the lower water volume fraction gives a more stable emulsion as it inhibits the formation of water droplets and gives off lower viscosity. Therefore, the 2080 water in crude oil emulsion is the most stable emulsion among the other ratios. With this characterization, we will be able to find the most optimum water to oil ratio, the concentration volume of the surfactant, and the type of surfactant to obtain the most stable emulsion for future findings of water in diesel to be used in engines. By reducing the oil ratio in diesels, we will be able to save the cost, preserve the environment, and preserve the amount of crude oil that already exists.